Good afternoon. I think we're ready to get started. My name's John Dutcher. I'm a professor over at the University of Guelph, which is a stone's throw away. I'm going to tell you today about kind of a fun story. This is a case of serendipity in the lab that has translated into really cool fundamental science and even technology transfer and commercialization. So what I want to do first of all is thank the organizers for the opportunity to speak here. When I got the invitation to speak here at a Women in Physics conference, it made me think back on my own education. And I realized to my chagrin that I have never had a female professor. It's ridiculous, but at the time, it wasn't so uncommon. So in university, undergraduate, master's, PhD, never had a female prof. So it made me think back to high school, and I actually benefited greatly from two really great women teachers in high school. And one was a math teacher, Miss Buck. She taught enriched math. She used to dazzle us with mental arithmetic, very inspiring. And Mrs. Whiteley, who taught the senior physics courses, was sort of a dynamo in the classroom and really helped to inspire people as well. Incidentally, it's sort of interesting that one of my colleagues at Guelph, Elizabeth Nicol, had the very same teachers. About 3 years later, she went through the same high school in Moncton, New Brunswick, and we both ended up as faculty members at Guelph. So you just never know. Okay, so what I want to tell you about today is this fun stories. So this is an example of what you might call nanotechnology from nature. It starts with a serendipitous discovery. And then, because we didn't know what we were doing, basically, we looked at it with as many tools that were available. And we found out that this molecule that we discovered has a very unique structure. It has a highly branched polymer structure, something called a dendrimer. And because of this structure, it has a very interesting interaction with water. And so we've used a lot of experimental techniques, some of which are new to us, to really probe that interaction between the molecules and water. And as anyone knows, water is really complicated, so this has been a lot of fun. At the very end, if I have time, I'll tell you a little bit about the technology side and how this has led to a spin-off company in Guelph, which has to date raised $20 million, and we're building a factory, so it's becoming real. So as I mentioned, this happened through serendipity. So this was actually part of a fundamental multidisciplinary collaboration between my group in physics and Terry Beveridge's group in microbiology. Terry was a world-class microbiologist interested in looking with high-resolution microscopies at bacterial cell surfaces. And our project dealt with the question, how do bacteria stick to surfaces? We know that that can be a problem. You can have bacterial fouling of surfaces, the buildup of bacterial biofilms. How does this actually happen from a combination of physical and biological and chemical effects? So as part of that project, one of the postdocs was doing a rather complicated multi-step chemical process. Basically, on the outer surface of bacteria, there is sort of a grass-like layer that corresponds to molecules called lipopolysaccharides. The lipo part sticks into the membrane of the bacteria, and the polysaccharides decorate the surface. And that's really the first line of defense against anything that might want to harm the bacterium. So if you're going to study bacterial surfaces, you're going to look at the lipopolysaccharide content. So in isolating the LPS, it generated a waste product in one of the steps. And it turned out that this had sort of interesting optical properties. So I show here a globe of these particles suspended in water. And hopefully you can see this. The globe here is lit from the left-hand side, and so it's blue in reflection and orangish brown in transmission. And because of this rather interesting optical property of opalescence, instead of throwing the waste out, Anton kept it. And eventually, after some time actually, we got around to looking at it using one of our atomic force microscopes. And it's one of those cases where you see something that's really quite interesting. So we expected to see a big mess. Okay? Instead, what we saw, which is indicated here on the left-hand side, are all of these little particles that are all very much exactly the same size, little balls, okay, that were about 35 nanometers in diameter. And that was a big surprise. And we set about using all of these different techniques to figure out what exactly this was. It has a highly branched architecture, as I'll tell you. They're very soft and compact. You can think of these little balls as having uniform surface chemistry. So in terms of what you can do to these things, you can use them as is, or you can decorate the surface with other molecules, changing their character. And the nice thing about this is that these particles are entirely biodegradable and even edible. A major step for us was to move from generating these particles from bacteria, which is really hard. Involves fermentation techniques. It's very painful, inefficient, difficult to scale process. We realized that similar particles were actually made by certain varieties of sweet corn. And then it becomes interesting from a technology point of view because you can now produce a nanotechnology in the field next door. So it has great technology applications, as I'll mention to you, but it continues to amaze us with really cool science. So the basic structure of the molecule is something called a dendrimer. Okay, so the way in which this grows is it starts with the seed in the middle, and then linear chains of sugars, just glucose actually, grow out, and then after a certain length they branch. Those branches grow and branch and grow and branch. And synthetic chemists are really good at making these things in the lab, although it's horrendously expensive. It turns out that nature does this on its own in certain organisms, including sweet corn. So this is the classic picture of a dendrimer, starting from the middle, and then the branches grow out, and the branches grow out. And you have, from this kind of picture, the impression that the molecule has a highly branched outer surface, and it's hollow in the middle. Well, that turns out not to be true because these sugar chains are quite flexible and nature abhors a vacuum, sort of. What happens is these sugar chains will just fold back in, fill in all of the available space within the molecule, and you end up with this highly branched molecule with essentially a uniform density throughout. And here is a computer simulation of a molecular dynamics calculation of the growth of one of these particles in which each generation between branching points is represented by a different color. So you can see the outside surface, and as it rotates around, you can see the different colors on the inside. And one thing you should notice is that the outermost generation, which is indicated by black, is actually visible throughout the entire volume of the particle. And that's because of this back folding in, leading to a uniform density. So this special dendrimeric or tree-like structure results in special properties. One property it produces is that as the particle grows and branches and grows and branches, eventually the enzymes that are responsible for the growth can no longer access the necessary sites, and the growth stops. And this leads naturally to particles that are all very much the same size. Other properties, and the ones that I'll focus on for today, involve this special interaction with water. Something that I would call extraordinary water retention, low viscosity when you add them to water, and very high stability of these suspensions of particles in water. So for example, in terms of retaining moisture, they're really quite special. This is a plot of something called relative water retention as a function of time measured in days. So basically, you just hydrate these particles, and then you stick them in a dry environment, a desiccator. And you measure how much water is there as a function of time, okay? And what you see is that, so they're all normalized to 1 at t equals 0. And now we have a comparison between these phytoglycogen molecules and 3 other common moisturizing agents in cosmetics. Okay, so 2 of them are petroleum-based and cheap, glycerol and polyethylene glycol, shown in black and green. The one in blue is something called hyaluronic acid, which is actually a very high-end, like the best moisturizing agent that you pay a gazillion dollars for in the store. And as you can see, the water retention by our molecules, which we call phytospherics, is greatly increased with respect to that. So from this point of view, you can see that you put water into these particles, and the water is really strongly retained. It holds onto water tenaciously and only lets it out very gradually. So in terms of a moisturizing application, it provides a slow release of water, which sort of tends to smooth out the effects of changing relative humidity, makes your skin feel nicer. Okay, so that's the application side. To try to understand what's going on with these particles in water, we used a large number of different techniques that are specifically geared towards understanding the interaction between water and molecules. A technique like neutron scattering. So we went down to Oak Ridge National Lab and scattered neutrons from these particles dispersed in water. And I won't have a chance to tell you about the details of that, but let me just say we learned a lot from neutrons. We were able to measure the particle size, the radial particle density, which we verified was uniform. We were expecting it to be hollow in the middle, and neutrons told us that it was uniform. Then we went back and were able to understand that. It also was able to tell us how much water is incorporated inside these particles. It turns out there's about 250% of the weight of the molecule in water inside the molecule. And even was able to tell us that the dynamics of the water inside the molecules was about a factor of 6 slower than it is in bulk. So this very confined environment for the water inside the particles led to slowed water dynamics. Another technique that's really great for studying water is infrared spectroscopy. And that experiment, you measure the absorption of infrared by chemical bonds. And if we focus on the OH bonds, we can learn something about the structure of water inside these molecules. Once again, I don't have time to tell you about this, but what we found from these measurements was that the water was highly bonded and highly structured within the molecules relative to bulk water. Another measurement that we can do is to make very thin films of these particles using a technique called spin coating, and then look at how these films swell and shrink in response to changes in relative humidity. And from that, we can learn other fundamental information, such as short-range hydration forces. But the thing I want to tell you about today is something called rheology. So this is basically measuring the mechanical properties of a material. Okay? In this case, we're looking at dispersions of these particles in water, okay, and measuring a variety of different things. What I'm going to focus on is just a measurement of something called the viscosity, right? So how thick is it as you add more particles? Okay, and what we find from that is that this is a beautiful, soft colloid system that provides a new window on the behavior of colloidal dispersions. So this is what I'm going to focus on. So what is a colloidal dispersion? Well, it's basically, a particle, microscopic, nanoscopic particle that's suspended in a liquid. Lots of important applications: cosmetics, foods like milk, like mayonnaise. Paints and inks are colloidal dispersions, agricultural sprays, even pharmaceuticals. So that's something that we see in everyday life. But another thing that is true of colloidal dispersions is that there's some really cool science. Okay? So for example, the opalescence that we saw for our particles suspended in water, cool optical properties. It's also possible to crystallize colloidal particles to create microscopic equivalents of crystals that would normally occur at the angstrom level, and to study phenomena like melting and freezing and jamming and all kinds of things like that. So let me show you what happens when we take these little sugar polymers and add them into water. Okay, so what I have here is a plot of the viscosity of this dispersion relative to that of the solvent, which is water. Okay, so that's what's plotted on this axis as a function of the concentration of the particles in a weight percentage. And as you can see, not much happens up until very high concentrations. In fact, this is a really lousy way to plot the data. It's a much better idea to plot the vertical axis rather than on a linear scale on a log scale. And then you see this beautiful behavior. As you increase the concentration from 0, you see a modest increase in the viscosity such that by the time you've made it out to 20%, it's only increased by, less than 2 orders of magnitude. And then eventually, at very high concentrations, it takes off and becomes very high, changing by about a factor of 1,000,000, ultimately, at extremely high concentrations. The way to understand that is that eventually you've added so many particles, kind of like this picture down here, that you've forced the particles into contact. Okay, there's so little of the water around, so you've formed a gel which is necessarily very viscous, okay, by adding so many particles. But what's really unusual about this is that if you take a normal polysaccharide, for example, you go into the kitchen, you're making a sauce, you want to thicken your sauce. What do? You add cornstarch, okay, another polysaccharide, right? Just sugar molecules connected together. You know that if you add in just a little bit, that the viscosity of your sauce will increase dramatically. Okay, that's why we use it. And that's represented here by this sort of representative point corresponding to another polysaccharide called guar gum. It's just another typical polysaccharide. And here you can see that after adding in only a couple of percent, you have, over 3 orders of magnitude increase in the viscosity. That's the kitchen effect, right? The sauce effect. That does not happen for our particles. Instead, you have to add up to about 25% of this stuff by weight before you see a comparable change in viscosity. What this means is that the particles essentially don't interact with each other until they come briefly into contact, hit, and then bounce off each other. Kind of like billiard balls that are indicated over here. And that's sort of reminiscent of something that's referred to as a hard sphere interaction, like balls bouncing off one another. Okay, so how do we measure the viscosity? Well, we use a technique called rheology. So probably not a technique with which you're very familiar, so let me just describe what it is. You have some kind of sample. It may have a low viscosity, it may have a high viscosity. Depending upon the value of the viscosity, you choose one of 2 geometries. So if it has a low viscosity, you put it between 2 concentric cylinders. The outer cylinder is fixed, and you rotate the inner cylinder. And in this way, you generate a flow field within the sample that lies between the inner and the outer cylinder. If it has a higher viscosity, a better choice is to use what's called a cone and plate geometry. So you put your sample down onto a plate, and you have a very low angle cone that comes in contact with it. You rotate the cone relative to the plate, once again creating a flow field inside the sample. So using these 2 geometries, depending upon the viscosity of your sample, you can generate a measurement of the viscosity. So in the case of very low viscosity samples using the concentric cylinder geometry. What you do is you change the shear rate of the motion, and you measure the corresponding stress. And from a plot of stress versus strain rate, you get beautiful data that looks like this. The slope of that plot is the viscosity, okay? And as you can see, the data gives you a very precise value of that viscosity. If it has a higher viscosity, you use this cone and plate geometry. It turns out that this particular type of sample behaves in a nonlinear fashion at very high concentrations. So at low concentrations over here, this corresponds to what's called a Newtonian fluid, okay? Stress is linearly proportional to the strain rate. That's not true at high concentrations. Instead, what we see is that the value of viscosity depends upon the shear rate, and as you shear it faster, you get a lower viscosity, and it drops off in a power law fashion, as indicated here. And this is called a non-Newtonian fluid, and this phenomenon where the viscosity decreases at high shear rates is something called shear thinning. And it's quite common for what are known as complex fluids. So what we have at high concentrations is something that is non-Newtonian in character. But we can fit this data to a variety of different models. This one is called the Williamson model. And basically, the best fit is represented by the solid line here. And the zero shear viscosity value is the intercept up here. And so what we're going to do is basically make a plot of the zero shear viscosity as a function of concentration, okay? Low values will be measured this way, high values be measured this way. We'll put it all on the same plot. And when you do that, oh, sorry, this is the data for different concentrations, okay? So this is all linear over here because it's low concentration. The slope of each of those data sets is the viscosity, which is also the zero shear viscosity. And over here on the right-hand side, we have the nonlinear regime where we fit to this model and extract the zero shear viscosity value as a well-defined plateau that you get at low shear rates, okay? So that's how we're going to collect this data, and this is what it looks like. And this is basically the plot that I showed to you before, a plot of the viscosity of this dispersion relative to that of the solvent water, so the relative viscosity on a log scale versus the concentration. The blue data points were collected using this concentric cylinder geometry, low viscosities, and the red data points were collected with this cone and plate geometry, and then we did some checks to make sure that we get the same values at this crossover region between the two geometries. So we can actually just replace the blue with the red. It's all one big data set because of the excellent overlap. Okay, so what do we make of this? How do we interpret this behavior? It's cool, but how do we relate this to theories? Well, the simplest type of theory that people use for understanding colloidal dispersions is the so-called hard sphere theory. This is the billiard ball model, where the particles don't see each other until they collide and bounce off of each other. This is theoretically very nice because the properties of such a hard sphere dispersion are defined by a single parameter, something called the volume fraction. The volume of the particles relative to the volume of the dispersion, okay? This thing called phi. And a long time ago, Einstein taught us that the viscosity of a dispersion is equal to the viscosity of the solvent plus a term that is linearly proportional to how much the particles are in the dispersion. Okay. That's valid for very low concentrations. If you go up to very high concentrations, then the particles start to see each other. You have to somehow account for those interactions between particles that ultimately leads to a big increase in the viscosity. And there have been various models that have been proposed to describe that behavior. This one that was developed by Krieger and Doherty has a form that looks like this. So if I make a plot of relative viscosity versus volume fraction, it kind of looks like the previous data set, right? It has low values at the small values of the volume fraction, and then kind of diverges as you go up, okay? And this is, once again, because at the high values of the volume fraction, you put so many particles in there that you force them into contact, and now instead of behaving like a fluid, it behaves more like a gel, okay? Okay, so simplest theory, how does this compare with what we have? Well, before we can make that comparison, we actually have to do a conversion between concentration and volume fraction, okay? Normally, that would be a trivial thing to do, but in the case of our particles, we have to work a little bit harder because these particles absorb 250% of their own weight in water. So when you add them into water, they suck up a lot of the water, which then changes the volume fraction of the dispersion. So it turns out that it's possible to make this conversion. You just have to work a little harder. It involves, quantities that you measure directly, like the mass of the dry particles and the volume of the water that you add, but other quantities that have to be measured independently. So the amount of residual water in the dry particles, it's never completely dry, but you can use something called a Karl-Fischer titration, which is something that's routinely used by chemists to measure that residual water content. And neutron scattering actually tells us the density of the hydrated particles. So using all of that information, you can calculate the corresponding volume fraction values. And now I can make a plot of relative viscosity versus volume fraction. And this is what it looks like. It looks very similar to the plot I showed before, except now, down here, we have volume fraction values. Now we can compare these results to this simple theory of hard spheres. Okay, so when we do that, this is what we get. Okay, big differences between the data set and the curve that corresponds to hard spheres. In particular, if you have hard spheres and you pack them in, there is a limit as to how much you can put in. If it was a crystalline solid, an FCC lattice, that maximum packing fraction is 0.74, which is what Kepler taught us centuries ago. Instead of getting crystalline order, what you get in these types of systems is something called random packing of spheres, which has a maximum packing fraction of 0.64 instead of 0.74. And so that corresponds to this divergence in the hard sphere curve right here. Obviously, these soft particles are behaving very differently, and it's this deviation at high volume fractions that is the most interesting thing. It indicates that the particles are deforming as you add more and more particles in. Okay? And the easiest way to see this is to sort of think of this schematic picture here. So this is the idea of making a colloidal dispersion, okay, and increasing the volume fraction. If you have, well, as you add more particles, eventually at some point they'll all kind of touch, okay? And that leads to this critical value of the volume fraction, which for hard spheres is 0.64. But if these particles are soft instead of hard, if you continue to add more material, then these particles will deform, and they'll form facets at the interfaces between the neighboring particles. And it's kind of like a soap bubble raft, right? Everyone has seen on the top of your coffee in the morning or in the kitchen sink or wherever, you see rafts of these bubbles that don't have any voids between them. They actually deform to remove all of the voids to be close packed. And as a result of that, you have these polygons that are in contact with each other at high volume fraction. What's the maximum packing fraction of these objects? Well, the point where you don't have any voids. So the point where you don't have any voids corresponds to a volume fraction of, any idea? 1? 1. Okay, and if we go back and look at our data, look at this. We have this divergence in the viscosity values, and at the maximum concentration that we used of 30%, we see a volume fraction that's very, very close to 1. So this is the point where all of the voids between the particles have been removed. Okay? So that's kind of cool, but we can do even better, okay? Because not only are these particles deformable, they're also compressible, okay? So it turns out that if you try to mix these particles into water, 30% concentration is about the maximum you can do without breaking your mixer. But there are other physical effects that you can use to achieve even higher concentrations. And there's something called osmotic pressure, something that tends to get neglected in physics courses. How many people have learned about osmotic pressure? Not too many hands. But it's a really important concept. And one thing that you can do is you can take a dispersion of our particles. Okay, so we're starting with a concentration that's fairly high, 25%, and you can place that inside a semi-permeable membrane, something called a dialysis membrane. Okay, so this is sort of the indication here. So this is a little dialysis cassette that you can buy from Fisher, and you put your dispersion inside of it, and on the outside, inside this beaker, you have what's called an osmotic stressing solution. So this is typically molecules of polyethylene glycol or dextran that has been added to some concentration. And there's a well-known relationship between the osmotic pressure and the concentration of polyethylene glycol or dextran. And this is due to somebody who spent his career at Brock University, Peter Rand. He has this ancient website, even though he's long retired, and this website is still thankfully maintained, and everybody in the world uses it for the calibration curves of osmotic pressure versus concentration of these osmolytes. Anyway, by changing that concentration of the molecules outside your dialysis membrane, you can either cause water to be transferred in to where your particles are, or transferred out. And so what we have here is a plot. So each one of these data points corresponds to a different experiment with a different concentration of polyethylene glycol. And you can see here that so the experiment is you set this up with a certain concentration and you wait 12 days, and then afterwards you open up your cassette and you weigh it wet, and then you dry it out, and then you figure out how much water was in there and therefore what the concentration was, okay? And by doing experiments like this, we can get way above 30%. So 30% is sitting right here. We've gone all the way up to about 65%, okay? Which is kind of neat. So this is an area that we continue to explore, but one thing that comes out of this quite naturally is, for a concentration of 30%, we have a volume fraction of about 1, as I showed to you before. And what this means is that all the particles are in contact, but not compressed. If you increase the osmotic pressure above that, they will start to compress. So to a very good approximation, the value of the osmotic pressure at that concentration where the volume fraction reaches 1 is the bulk compressional modulus of the particles, which is about 20 kilopascals, which is kind of a cool. So there's all kinds of information that you can get out of these sort of mechanical measurements. I better stop. Do I have time to say a little bit about the technology? Okay, sorry. This is actually kind of fun. It's very gratifying to, discover something in the lab, look at it, discover that it's actually genuinely interesting from the science point of view, and then find out that it also has really important applications. So we bumbled our way along this path, having never done it before, But I managed to get quite a bit of funding, over $1 million in funding, to evaluate the technology in my University of Guelph lab, discovering that we could generate these particles from corn and non-GMO corn, which is really important. They actually gave me money to grow corn in Elora to figure out which varieties of corn gave the best yield of these particles. And we went out to Saskatoon and did a pilot scale production of tens of kilograms of this stuff. Okay? So that's pretty neat. Basically showing, and then in addition to that, showing about 10 or 20 different proof of principle applications of these particles. At that point, we decided that this was a real technology. We didn't want to license it to a large multinational company. We thought, we can do this ourselves. And so we created a startup company called Mirexis. Okay? And Mirexis has done well. We have intellectual property that's protected by a whole patent, or whole portfolio of patents, including structure of matter, as well as lots of applications. We were smart enough about 3 years ago to realize we cannot do this ourselves within a university, and so we hired a business person who actually has a PhD from McGill in science. And so he gets the technology, he can make the business side happen, and we've managed to raise almost $20 million, including $12 million just 2 months ago, that we will use to build a factory in Guelph to produce these particles at a scale of up to 15 tons per year. The nice thing about this is that we have approvals for use in cosmetics, something called EcoCert, and food. Health Canada approved our material as a food ingredient in 30 days, which is sort of unheard of, actually. But the argument you make is simple, right? It's like, well, it comes from corn. People have been eating it for centuries. And all you have to do is ensure or tell them and convince them that you've done nothing to add anything bad to the material in the extraction process. But the nice thing about this is that the corn does all of the hard work. It makes the particles. All we have to do is extract and purify them without destroying their special properties. So the company has 3 main efforts. One in personal care. The leading application is a moisturizing agent in cosmetics. But recently, we ran a trial that showed rather remarkable anti-aging effects. So I don't know if you know what that lingo means. Basically, it gets rid of wrinkles. So that's huge. That's much bigger than moisturizing, actually. There are some interesting things you can do on the food side, specifically nutrition. You can have delivery of bioactive molecules, so-called nutraceuticals. And perhaps the most promising area is in the area of biomedicine or healthcare. And we've been able to demonstrate that we can create some novel antimicrobial compounds by modifying the outside surface of these particles. We can deliver drugs using these particles, and the nice thing about that is the drug delivery vehicle goes away. It doesn't accumulate in your body because it's just glucose. And we have enzymes that will break that down. And so it's sort of the ideal drug delivery vehicle. And then unexpected effects that I don't understand that will either upregulate or downregulate the immune response of organisms for modified versions of these particles. So the biomedical side, as with a lot of technology, shows the most promise, but of course it's the longest to be realized. So. Opportunities for physicists at Mirexis. So, this came out of my lab at the University of Guelph, so they actually hired a lot of my people. And so there are quite a few, an extraordinarily large fraction of physicists within the company. Here we have a picture from the first big cosmetics show that the company attended in Barcelona, something called In Cosmetics. This is the place to be. This is Alison Krumbelholm, who is now our VP of Business Development. Over here on the left is Marty Krylovitz, who has a PhD in physics and was a postdoc with me, and now heads the R&D effort within the company. This is Carly Mickey, who was a nanoscience student at Guelph with a specialization in physics, did an MSc in physics and then was hired on, and now she works in both the R&D and the sales side. And there are even opportunities for physics co-op students. So this is a picture here of the two of the co-op students that are presently working at Mirexis. These are my two daughters. I didn't hire them. This is Lauren in the front and Megan in the back, and they're both third-year physics students at the University of Guelph. And so they've had a great time getting their practical experience at the company. The president of the company, Phil, likes to say that finally we're getting something useful out of a Dutcher at Mirexis. So anyway. So I will finish, and sorry for taking so long. I've told you about this natural nanotechnology. It's safe, it's non-toxic, it's even edible. It's because of the special structure, this highly branched dendrimeric structure, that the particles have very special properties. And in particular, a unique, strong interaction with water. And what this means is that we have this promising new material that we can use not only for really cool fundamental research, but also new technologies. So with that, I will just put up a list of people who have been involved in my lab over here, at the company Mirexis, and at Oak Ridge National Lab, where we did a lot of the neutron scattering work. Thanks.